So, good afternoon, everybody. Welcome to the last lecture of this course. I think I will be able to cover everything about chemical sensors today. There is not much about that. First, I will reply to the answers that you had in the test last week, and then I will have a small note about the previous lecture, and eventually we will study chemical sensors. And tomorrow we can have some exercises together. Then this will be the last actual lecture for this year, because then there will be Christmas holidays. And we have an extra week, the 14th week of the semester will be the first week of January. I don't remember if the first or the second. I think the second week of January. Anyhow, it's all in the academic calendar on the faculty website. And in that time, we still have the 14th week of the semester. We will make a session of question and answers. What does it mean? It means that during the Christmas holidays, you will have some time to revise everything we have studied so far. And, sorry. And you will make down a list of questions. And then you will send it to me. Either, typically the session of question and answers is made live. So it's very productive because students arrive with a list of questions and we discuss them together. For this time, it's kind of difficult to send the questions over Teams because communication is not so easy. So I would rather ask you to send me a list of questions detailed before, so that I can read them and see in details what you need, and so that we will not waste our time when we are having this session of question and answers. Okay, so I please ask you to prepare during the Christmas holidays. Just study everything we have done, list down the things which are not clear. Of course, don't ask me, okay, could you repeat everything about sensors of temperature? That's about a couple of hours of lecture, so I cannot definitely repeat a whole lecture. But if there is a specific topic that is not very clear, or maybe some details which you cannot get, or maybe I was not good enough in explaining that, please list it down and send me the list of questions so that we can study them together again, okay? So we will have 2 extra lectures on Thursday and Friday in the first week of January, when we will be focusing on this exercise of frequently asked questions, okay? Fine. Before starting with the lecture, I said I wanted just to point out, I just wanted to talk about the test. Generally speaking, it was good. The results are quite good. There was one student who managed to make all 4 questions correctly. IAG. I cannot mention the name. I just say the initials. So congratulations to you. And the most common error was done on question number 1, or maybe it was another question because the questions were shuffled. And it was the question about absolute sensor of vibration. The question was an absolute sensor of vibration as a response equivalent to the acceleration if used at a resonance frequency, which is wrong, at a frequency higher than the resonance frequency, which is as well wrong, at a frequency lower than the resonance frequency, which was the correct answer, and the 4th wrong answer was both at the frequency below and above resonance. I saw that many of you answered not correctly to this question, so probably I would better repeat a little bit this topic because evidently I was not able to make it clear enough. The sensor of vibration, absolute sensor of vibration, is this one. The implementation was with the seismic mass, typically with some piezoelectric sensor. We have seen several implementation, and this is the model. So the model is composed of a mass, which is connected to the structure, the frame of the sensor, and the model of the connection is provided by a spring force, so a force which is proportional to the compression. So if you take the coordinate x of the seismic mass compared to the frame of the sensor, the larger is the compression, the larger is the force which repels the seismic mass, so it's a spring force. Then there's a damping. So the damping says that the force is proportional to the velocity. If the mass is still, you don't have any force. But the faster it moves, the faster, the larger will be the force. Okay. And then there is, of course, m times the acceleration, which is the inertial force of this mass. Okay. Then when you move, so the principle of the sensor is that you move this case, okay, this large case, of a coordinate x of y. So you vibrate your sensor with the coordinate y of t, okay? So it moves with the coordinate y of t as a sine wave with a certain frequency. Then, and so you have this vibration y of t. Then inside, there will be a mass which behaves in a different way according to the frequency of y, okay? So what does it mean? It means that inside the sensor, okay, this was one part which for some of you I've talked to last week was not clear. So what you measure is x, and you measure it by using, for instance, a piezoelectric sensor, okay? So inside the sensor, you measure the coordinate x of t with, for instance, a piezoelectric sensor, which tells you how the seismic mass moves compared to the frame of the sensor, okay? And then, from x, you must be able to retrieve the value of y, okay? So you directly measure x inside the sensor. So if you have your frame here, let's say that this is your frame of the sensor, you can measure directly the coordinate x of t, how it moves in time, of the mass with the respect of the frame. So it will, if it moves like this, you can measure x prime of t, okay? So the mass can move inside the frame and you can get x of y. But then you must be able to detect y, which is eventually the coordinate you are interested in. So with respect of an inertial system, you want to know how the sensor is moving, not how the mass is moving inside the sensor. Your ultimate goal is to find out how the sensor, the vibration of the sensor, so y of t, okay? So, but you measure x. So from x, you must be able to go to find y. So if you plot the transfer function, so x divided by y, so the transfer function between x and y, you find out, and you plot it for different frequency as a function of the frequency, you find this graph. And to be more precise, we plot it as a function of the normalized frequency. What does it mean? It means that we plot the graph, and on the horizontal axis here, we have, let me open here because, okay. And on the horizontal axis, we have the frequency divided by the resonance frequency. So psi here is the frequency, or in this case, omega 2 pi f, divided by the resonance frequency omega 0. So in fact, here you see that you have resonance at 1, because at 1 it means that you are at resonance frequency. Omega is equal to omega 0. Omega 0 is the resonance frequency, okay? And What does it mean? It means that if you are in resonance, it's just enough to have a very little y, that the amplitude of x becomes enormous. Ideally, if there is no damping, it becomes infinite. So here you see that, for instance, here at resonance, if you have a very small y, then x becomes very, very large. So it means that this mass inside the sensor, if you move the sensor by a small y, this mass will boom, 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 will destroy the sensor, ideally, if it's too large, because it's in resonance, okay? So a very small change of y will cause a catastrophic change of x inside. So definitely the answer was not in resonance, because the only thing you do in resonance is to make this x become extremely large, so the mass inside becomes extremely large, even if you have very small y, okay? What happens out of resonance? We have two regions. For a frequency which is much smaller than the resonant frequency, so we have psi much smaller than 1. It means for a frequency much, much lower than resonance. So the frequency is much, much smaller than resonance. What happens? This equation, so x omega t divided by y omega t, the modulo, and let me copy it because my memory at my age is getting short. So it's 1 over psi squared, if I'm not wrong, yes, plus 2b psi squared, okay? And here we go. So what happens at for psi much lower than 1? So this is psi squared. So if psi is much lower than 1, definitely psi squared is even way lower than 1. So we can approximate it to 0, or generally speaking, no, this is not a very nice thing to do. I would rather say that we neglect this and we approximate it this to 1, okay? Because compared to 1, psi squared is almost 0. So let's say that this is 1. This is also very small. So we approximate it to almost 0. So what we get here? We get psi squared divided by square root of 1 squared, which is only psi squared, okay? So for very small frequency, what you get is a response, a transfer function, which is proportional to omega squared. Omega squared is the acceleration, because if you have a sine of omega t, if you take double derivative, the second derivative, not double, the second derivative of a sine, then you end up every step of the derivative you take an omega outside, so you have omega squared, okay? So omega squared in a sine wave is proportional to the second derivative, and the second derivative is the acceleration, okay? So for low frequency, you have acceleration. So the answer was for frequency sufficiently lower than the resonance frequency. That's where you have a behavior, a transfer function, which is proportional to the acceleration. Okay. Of course, this is an approximation. It depends also on the damping. Okay. So First of all, it depends on the frequency, because, and in fact, when you buy one of these sensors, they consider the bandwidth of the device responsive to the acceleration as 1/10 typically of the resonance frequency. Okay, so in order to consider this sensor actually a sensor which responds to the input, giving as output a signal proportional to acceleration, you have to stay in where the frequency is at most 1/10 of the resonance frequency. Okay, so for instance, if you have 0, 1 here, this becomes 0, 0, 1. Okay, so then you can really neglect it. And then, of course, it depends also on the damping. What happens at high frequency? At high frequency, simply let's remove this. This becomes again psi, and this is psi squared. Now, here I have psi squared, which is much larger than 1. If psi is larger than 1, psi squared is even more larger than 1. So here I have psi squared squared. Okay. Then, so this can be approximated at psi squared. This is much negligible than this one, because then here I squared, but then I square it again, and here I have only psi squared. Okay, so eventually you turn out to have psi squared on the numerator, and here you have psi squared squared, but then under the square root. Okay, so you have, let's say, psi squared squared under the square root. So eventually you have psi squared divided by psi squared, and you get 1. Okay, which means that x is proportional to y. Okay, and that's the point where the sensor measures simply the position. So the output is not proportional to the second derivative anymore, but it's proportional to the input. So it measures the position. Okay, fine. About the other questions, very quickly. Let me find where they were. The other questions were way simpler. So question number 2. Oops, mistake. So the second question was, an eddy current sensor can detect what? The answer was correctly a conductive material. The current sensor is based on the fact that you have a conductive material, you create an electromagnetic field which induces at a certain frequency some eddy currents in the conductive material, and then you can detect the back field created by these eddy currents with a pair of coil, and you can detect this back field only if you have these eddy currents. And you can have eddy currents only if you apply a time-varying magnetic field to a conductive material. Otherwise, the current cannot circulate. If you apply time-varying magnetic field to something which is not magnetic, you will definitely not generate any current. Okay? So definitely the material should be conductive. Then 2 answers were non-conductive material, which is obviously wrong, and ferromagnetic material. Here I said only a ferromagnetic material, which is wrong. Ferromagnetic material typically is conductive, but it doesn't need to be a ferromagnetic material. It could be also copper, for instance, which is conductive but not ferromagnetic. Okay. Then we had question number 3, and let me see. It was metallic strain gauge. And the correct answer is that it has a resistance which changes because of the change of length and cross-section. Here I specify the metallic strain gauge because, as you know, there are also semiconductive strain gauges which, on the other hand, have a response depending also on the piezoresistivity effect. Okay, so in semiconductive strain gauges, you have also the resistivity changing for the force. For metallic strain gauges, is mainly due, the effect is mainly due by the geometric change of length and cross section. Okay, and then eventually the last question was a thermal mass flow meter based on NTC thermistor operated with a constant current as an output voltage, which increases as the flux of the cooling fluid increases. Okay, remember you have an NTC, you warm it up, injecting a current. This current will decrease. If you remember here, let me draw it. So here you have the current, here you have a voltage. At high current, so we get this constant current. We inject a constant current. The current bends down the characteristic because the slope of the characteristic is the resistance. And of course, if you warm up an NTC, negative temperature coefficient sensor, the resistance goes down. Okay. So if you have the temperature which increases, the resistance goes down. So if you use large current, the resistance will be low. But then if you have an increasing flux of cooling fluid, the cooling fluid will decrease the temperature, so the resistance increases, and eventually also the voltage, which is proportional to the current, and the resistance will be large. Okay, so it's enough to inject a constant current and check at the voltage. Okay, fine. One of the wrong questions was, can operate only if the fluid contains positive and negative ions. This was intentionally misleading because you know that there is another flow meter, which is electrodynamic flow meter, which is based on the fact that you apply magnetic field on a fluid, for instance water, where there are ions, and as the fluid goes under the magnetic field, the positive and negative ions will change position because of the force induced on the moving charge by the magnetic field, and therefore you get a voltage. Okay, so but that is a principle which is used in another flow meter, which is based on magnetic field, not on the flow meter based on NTC thermistor. Okay, fine. Generally speaking, I repeat, it was quite good. I'm satisfied of that. I'm satisfied by the result. So everything is fine. Now, before going to, so this is okay. Before going to chemical sensors, just rewatching the lecture of last week, I realized I probably didn't mention how to use this pyrolytic sensor. We were talking about contactless measurement of temperature, if you remember. And I mentioned there are these pyrolytic sensors, which are based on the fact, again, the principle is similar to the one of the piezoelectric sensor. Piezoelectric sensors are the ones that you compress and you get a change of charge due to the force. In this case, the change of charge is given by a change of temperature. And I say that unfortunately, they can detect only change of temperature, as well as the piezoelectric sensor that you must compress and change the force, otherwise, after some time, the charge will get in equilibrium again, passing through the resistance of the sensor itself. The same applies for pyrolytic sensors, so they can only change, they can only measure a change of temperature. And that's why, for instance, I was saying that this sensor here in the room, if you move slow enough, they are not able to detect a change of temperature due to the body. A pyrolytic sensor I use very often in this sensor of security that you find all over the faculty, for instance. And I say that if you move small enough, the change of a temperature of my body cannot be detected because I'm moving very slowly, so I'm below the frequency where the change of temperature can be detected. So again, if this is too fast, but if I move slow enough, it will not able to detect me, okay, like this speed. If I move like this, it's too fast. Fine. How to solve this problem? One thing you can do is to modulate the quantity of temperature, the quantity of heat which arrives to the pyrolytic detector. So if you have your sensor here, what you do is to create, for instance, a gear which rotates. Now, pardon my poor drawing skill. So this gear rotates and periodically covers the sensor, okay? Okay. So even if you have a constant value of heat arriving to the sensor, and generally you wouldn't get any response because it's constant, then you modulate it with a certain frequency by covering the sensor with this gear. So once the tooth arrives in front of the sensor, you will cover it, so you will get zero response. And then it will change again. Once you expose it to the heat, it will again get some heat and it will get some response. So even if you have a constant temperature, you can modulate and give the value of the constant temperature for some time, like here, and then zero when you cover it, okay? So you have a change of temperature, and you can get as a response an output which is proportional to the amplitude of this change between 0 and what you want to measure, okay? So again, the principle is always the same. You take something which is constant, and you impose a frequency, and from the output you will get a response which will be at the same frequency that you impose, in this case by forcing the heat to be 0 by covering the sensor periodically. And the amplitude of the output, as I told you, will be at the same frequency, but the output will be proportional to the amplitude, okay? So at the output, you will have a response which has the same frequency of this gear covering the sensor, and an amplitude which depends of the amount of heat that arrives to the sensor when it's exposed and not covered, okay? So this is, principles are always the same when you work in sensors. There are a few principles which are always repeated, and modulation is one of them, okay? It can be used in different methods, and one of them is exactly to take a constant value and to modulate it in order to have a response at a specific frequency. And it can be used for sensors which are responsive only to values, to physical quantities at a specific, at a frequency sufficiently large, okay? Okay, let's now study something about chemical sensors. About chemical sensors, there is and then there are really a lot of different sensors. We will just mention some of them just to give an overview of what you can do when you want to measure some chemical properties, okay? The first one we will study is the resonance piezoelectric sensor of gases. And it's based on a surface acoustic wave. Probably if you have studied something about sensors before, oh, I have to open here again. Let me see, where I do get it? Okay, I'm lost in the, here, sorry. Fine. So if you have studied something about sensors before, if you have attended a conference about sensors, I don't know, probably it's not very common for you, but if you go to a conference of sensors, definitely you will find several sensors presented based on surface acoustic waves. Why? Because they are very interesting devices which can be used to measure a multitude of different physical quantities. In this case, we will use them. So don't be surprised to see that even if you go, it's not necessary to go to a conference, but it is sufficient to go on Scopus, on Google Scholar, to search for papers. If you type surface acoustic waves, you will have an incredible amount of papers describing different sensors based on surface acoustic waves. Basically, these devices is, oh, maybe I should increase. Surface acoustic wave delay line is basically composed of a piezoelectric substrate. Again, we work again with piezoelectric substrate and two pairs of electrode. You know, piezoelectric material is a material. We've studied them when we wanted to start to investigate the possibilities to measure force using piezoelectric effect. And I say that a piezoelectric material is a material that, when it's compressed, you get a charge given by the fact that you compress it, and you have a displacement in the structure of the charges of the material. And if you remember, I said that in this case the output is charge, which means that you must be careful. You cannot measure directly the voltage because it depends on the capacity. Depends on the capacity of the sensor, the capacity of the cable. Therefore, you have to use a charge amplifier. So you convert directly the charge of the piezoelectric sensor into a voltage using a fixed value of capacitance in the feedback of the operation amplifier, so that you know exactly which is the capacitance used to convert the charge to the voltage. Okay. Fine. And so, if you apply a force, you get a charge, and therefore a voltage. But the same applies vice versa. If you apply a charge, then you can get a force. So it can be used as a sensor to detect the force applied to the piezoelectric material, but it works also as an actuator. So you can create a force by applying a charge with some electrodes. And that's exactly what happens here. In a surface acoustic wave delay line, what happens? You have a piezoelectric substrate, is an elastic substrate, where you have two pairs of electrodes. On one side, here, you will apply a signal to generate a force. So you apply there a voltage, and then it will create a force. And this force will create, it's a force with that, as you will see later, we take it in oscillation. So it will be AC, of course. As I said, everything must work in AC. So the force that we create here will create a surface acoustic wave which propagates along this substrate, which is elastic, as I said. So after some time, you will get here at the end, at the other end of this of the substrate, the surface acoustic wave, which deforms. Really, this is something that I'm simplifying. So just imagine that this wave here. There are the first electrode. I apply a signal here. This will perturb this, the substrate, and after some time, this force, this deformation, will create a force on the second pair of electrodes, and then you will get a signal. Okay, and you say, very interesting, but how can we use it to detect gases? Well. As a matter of fact, it takes some time the wave to go from the first pair of terminals of contacts where we create the force to the second one where we detect it. Okay, and this time depends on the mass that you have on the substrate. Okay, so basically the main component of this sensor is a membrane which is designed to attract specific gases. Basically, 90% of the art in this sensor is to create a membrane. The surface acoustic waves are very well known and very well studied devices. The key point here is to create a membrane which is able to attract specific gases. So what happens here? When you have a membrane and you have which is designed specifically to attract some gases, and there's this gas around in the place where you want to measure the concentration of that gas, basically the membrane will attract the gas and it will increase the mass on the substrate which composes the surface acoustic wave delay line. Okay, so basically we add some mass on this substrate by having a membrane which is able to attract a specific gas. Okay. So how do we practically use this sensor? As a matter of fact, we use them in a feedback, which means that here, let's forget about the fact that I have a second oscillator. Let's consider only one oscillator at first. Here I have the pair of terminal, here I have the membrane, and here I have the receiver. Then I amplify this voltage, and the feedback with the voltage, the first pair of terminals where I create the surface acoustic wave. Then I have a delay, which is influenced by the mass on the membrane. I have a receiver, and then back. So I have this feedback where the sensor, the response that I get from the second pair of terminals of electrodes, then will be amplified and feeds back. It will feed back the first pair of electrode, creating a resonator. Okay, a resonator which will resonate at a natural frequency, which depends on the delay that you have from the beginning to the end of the surface acoustic wave resonator. Okay, so basically, I will change the frequency of this resonator by changing the delay between the time it takes for the surface acoustic wave to go from the first pair of electrodes to the second one. And if we change this delay line, if you change this the time, the delay between the first, if you change the time, the surface acoustic wave goes from the first pair of terminal, first pair of electrodes to the second one, then you change the frequency of oscillation, okay? And how do you change this delay? By changing the mass that you have on the membrane, which is determined by the gas absorbed by the membrane, okay? And because it's not easy to change it's not easy to measure a change of frequency, what we do actually is to use another resonator based again on surface acoustic wave delay line, but without the membrane. So this one will have always the same delay because the mass on this substrate will not change, even if there is the gas around, because there is not the membrane which attracts the gas and then changes the mass on the substrate. So this will have a frequency, this again is in feedback, so it will again oscillate. It will have a frequency which is constant, whereas this one will have a frequency which depends on the delay of the delay line, and it depends on the mass of the gases attracted by the membrane. Then, as what you do typically when you want to measure the change of the frequency is to multiply these two frequencies, and if you multiply two different frequencies, you remember that you get the sum and the difference of the two frequencies. You don't care about the sum, but you care about the difference. So you get F1 minus F2, okay? Fine. Another similar sensor is based on quartz microbalance. Quartz microbalance is a very interesting physical effect, which was discovered by Mr. Sobery. I apologize if the pronunciation is not correct. When he was making his PhD, and it's very often used to measure very small quantities of mass. For instance, in if you are depositing very thin substrate, or you are dealing with, like in physical vapor deposition, for instance, you really need very, very precise way to measure the mass. And this gentleman found out that if you change the mass on a crystal oscillator, you change also the frequency of resonance of that quartz. And in fact, he even developed. First he showed it experimentally, and then eventually he even managed to describe the change of frequency as a function of some parameters of the quartz. So there's the active area between the electrodes, there's the density, the shear modulus, and these are just properties of the quartz. Then you have the resonance frequency squared, and then the change of mass. What does this equation mean? It means that if given this, by the way, this resonance frequency is the resonance frequency without any additional mass, okay? It means that if you change the mass on a quartz, you will have a resonance frequency which changes by a quantity delta F, which is proportional to the mass, which is good, because then you can derive from the change of frequency how much mass was deposited on the quartz. And interestingly, it depends on the square of the frequency, of the natural frequency, which means that you want, you want this sensor to have, you want this quartz to have extremely large, or generally speaking, very large frequency, because then if you double, for instance, the frequency, you get a response which is 4 times bigger, okay? So we need very high resonance frequency. And this principle is used in a lot of sensor for gas, again, because the principle is that what you do is to create a membrane which is selectively attracting some specific gases in order to have some extra mass on the quartz and significantly change the frequency and detect the amount of gas attracted by the membrane. Again, the principle is the same. In the previous example, the membrane was attracting gases which change the delay line, the delay line, okay? Here we, again, take this membrane, we put it on a quartz, and instead of changing the delay in a delay line, what we do is to change the resonance frequency of the quartz oscillator, okay? And there are plenty of different sensors based on this. Again, the art here is to create a membrane which is able to attract the specific gas you want to measure. So, for instance, here I just put the digital object identifier of some papers. You can find and read just for fun. Here, for instance, in this paper, they publish a sensor with titanium oxide nanoparticles, which is supposed to attract carbon monoxide and nitrogen dioxide. And just to give you, I just put it there just to give you an idea of the numbers that you can meet in this kind of sensors. Just to have more or less, just to know more or less which are the quantities of what you can measure. Here the sensitivity is about, for this sensor, they published a sensitivity of 1.25 nanograms per hertz. It means that the frequency changes of 1 hertz if you change the mass of about 1 nanograms These are numbers that typically you obtain with typical numbers for quartz oscillators. So if you have, for instance, 10 megahertz of resonant frequency, then you have typical density of quartz, a typical area of surface area between the electrodes. So if you put down some numbers, you find out that you find this kind of sensitivity. So as you see, they are intended to measure extremely small changes of mass. Okay. Here is another example, which is based on this cryptophane, a membrane to or substrate to abstract methane. Okay, CH4. And just to give you an idea of the frequency, how the frequency change, here you have the frequency versus the time. In this experiment, what they do simply is to alternate nitrogen. So here, when you have the high frequency, is when you have nitrogen exposed to the sensor. The quartz is exposed to nitrogen, and then here they inject methane with different percentage, with different concentrations. So 0.05%, 0.1%, 0.2, 0.3. As you see, when you arrive to 0.3, then it doesn't increase anymore. But for lower concentration, you see that the frequency is reduced as you increase the mass of methane absorbed by the substrate on the quartz. Okay. As you see here, the frequency is decreasing. It's decreasing because here there's a minus in this equation. Okay, so the frequency gets lower as you increase the mass. Now, of course, when you design this sensor, you want to add as much as possible mass to the sensor to have a bigger response, to have a bigger change of frequency. So from one side, you want to cover the quartz with as much as possible a membrane able to attract the gas. But if you load too much, then if you put too much on the quartz, then the quality factor of the quartz is getting worse. Okay, so you have this trade-off. And another important thing to mention, this sensitivity might be slightly misleading, because one might think that then you can measure down to this very small quantity of 1 nanograms. Always, this is the sensitivity. It doesn't mean it tells you how large is the response. It's the slope of the response, which tells you how much change of frequency you get per unit of mass changed. But you must always consider there is some noise. So typically you have always some hertz noise. So you must consider that the ultimate limit in measuring the smallest quantity of mass is given also by the noise, the frequency noise of the quartz oscillator itself. Okay, fine. Now there are a lot of other principles that are used to measure presence of gases, and most of them are principles we have already seen in the past. For instance, you will see that principles are almost always the same. For instance, we have this sensor based on thermal conductivity. Different gases have different thermal conductivity. So what we do is like in the thermal flow meter. Thermal flow meter, we warm up a thermistor and we observe the change of the resistance given by different cooling of water, for instance, flowing in the pipe. In this case, we do more or less the same thing. For instance, we have a platinum wire. We feed it with a constant current. We have two actually platinum wires. We put them in a bridge, like here. And then we expose them to a gas which enters from this pipe, arrives here, and it fills this this space where you have these two platinum wires, okay? And then on the other side, you have on the other two elements of the bridge. Here, if you observe, it's like you still have a bridge. It's horizontal, not vertical as we do as usual, but it's still a bridge. So you inject the current, half of the current goes here, half of the current goes here. So you have I0 in both legs of the bridge. You have 4 platinum wires. 2 of them are exposed to a specific gas that you want to measure the thermal conductivity of, and the other 2 are exposed to a standard gas, okay? And you warm up these 4 elements, these 4 platinum wires, and if you have different thermal conductivity, then the heat produced by the platinum wires will be taken away more from the platinum wires exposed to the gas which has higher thermal conductivity, because here you produce some heat with the platinum wire. If the platinum wire is surrounded by something which is very thermally conductive, it means that the heat can be taken away more easily, okay? If the gas is not thermally conductive, the heat cannot go anywhere because it's not thermally conductive, the gas, okay? And as you change the temperature, so the one exposed, the filament, the wires exposed to the gas with higher thermal conductivity will release more heat, then their temperature will go down, and therefore you have different resistances for the gases, for the wires exposed to the gas with larger thermal conductivity, because they will cool down, than the other resistance, and then you get the difference using a bridge. This is a typical configuration for a quasi-static gas. For fluxes, it's typical in some chemical devices that you have some considerable flux and you want to measure the concentration of specific gases in a reference flux. So the principle is always the Wheatstone bridge, and then one electrode will, one thermistor, one platinum wire, for instance, will be exposed to a reference flux, which means that a gas of a known composition, so a gas of a known thermal conductivity, and on the other hand, you will have a measured flux, which means that you have a flux, a gas, where the composition is slightly different. You have inside other elements. Now I can maybe show you here this table. Typically, the carrier gases, like the gases that you use for these experiments, you have some gas, and then you want to measure the concentration of another gas inside that because of the chemical processes that are running. So the carrier gas are like hydrogen or helium, which have generally for all temperatures, but let's focus here on 300 Kelvin, which is kind of room temperature. They have a thermal conductivity which is 1 order of magnitude larger, like in this case 156, 187, than the other gases. You see, if you watch the ammonia is 25, nitrogen 26, and so on. So if you have, for instance, a pipe with helium or hydrogen, it has this large thermal conductivity. If you inject some percentage of other gases, then the thermal conductivity will change, and you can detect this equilibrium by using this system. In this case, even if typically what you want here is to use this system where you have some flux, okay? So if there is a considerable, it's not quasi-static, but the gas is moving itself, it will have a cooling effect just because it's moving, okay? So you want to get rid of the change of thermal conductivity given by the fact that the gas is moving itself. So if it's different flux, then it will cool more or less. But if you have the same flux of the fluid in both cases, then you get rid of this effect because it will change in both cases, okay? In both the reference flux and the measured flux. Now, let me drink a moment because I'm getting I forgot to bring my tea today. Okay, very interesting effect is the very interesting system to measure oxygen, for instance, is to use the fact that oxygen is paramagnetic. You know that materials can be divided in ferromagnetic, cobalt, iron, nickel, which have a very large response to magnetic field, and typically it's non-linear response. At some point they get saturated, and when you remove the magnetic field, you still have a memory of the applied magnetic field because you still have the material magnetized, and this is ferromagnetic. Then there are paramagnetic. Paramagnetic are materials which do not have this huge response like ferromagnetic, but still they react positively to the magnetic field. So you can somehow observe a response which is positive. So the magnetization increases when you increase the applied magnetic field, and the ratio between the magnetization and the magnetic field is called susceptibility. I knew I was going to fail. Susceptibility. I will call it key because typically it's the Greek letter used to call this this word. And quite interestingly, and then there are diamagnetics, which means that the response to the magnetic field, so the magnetization that you obtain when you apply some magnetic field, is very small and typically negative, okay? Quite interestingly, oxygen has a susceptibility, I managed to say it correctly, I hope, which is much larger than other, and positive, than other common gases, okay? So given a susceptibility of 100 for oxygen, so this, I just listed there some values of relative magnetic susceptibility of common gases compared to oxygen. So I said oxygen equal to 100, and then let's see other gases, how they behave compared to oxygen. So the susceptibility of oxygen is 100, and then let's watch the others. Well, air, as you might expect, is 21 because that's more or less the percentage of oxygen in the air. All the other gases have a very small and negative susceptibility, which is, and that's why they are typically diamagnetic, okay? They are not paramagnetic like oxygen. There is the case of nitrogen monoxide and nitrogen dioxide, which have quite a considerable magnetic susceptibility. Be careful, not nitrogen, okay? Nitrogen itself is diamagnetic. You see here negative 0.42, but nitrogen monoxide and nitrogen dioxide, they are in fact, they can be considered basically paramagnetic. Fine. So how do we use this principle to measure the presence of oxygen? A very funny and fascinating method is to use the magnetic force created by oxygen under some magnetic field, okay? A force which the oxygen creates on other materials which are not paramagnetic like it. Here, this is the basic system of this sensor. Basically, you have two magnetic poles. Again, I apologize here, but the symbols here are still in Czech. S stands for sever, which is north in Czech, and J stands for he, which is south. And you create some magnetic field here with these two poles. Inside, you have this dumbbell where you have some under this magnetic field, under these poles where you create the magnetic field, you have some ampules which contain nitrogen. Okay, nitrogen has a susceptibility of like here. Let's compare it. Let's watch it here. Nitrogen has negative 0.42 compared to 100 of oxygen. Okay, so it's not only negative, but it's also 2 orders of magnitude. No, 1, 2, 3 orders of magnitude lower than oxygen. Okay, so when you create some magnetic field there, typically with some permanent magnet, and if there is nothing else around, you have this device which is suspended, like this cross here is suspended on some wires, okay? And these ampules containing nitrogen are there naturally under the magnetic field. Then the oxygen arrives, and the oxygen will arrive under the magnetic field. Then definitely the oxygen will take the place of the nitrogen. Why? Because if you have something which is not ferromagnetic, fine, but at least it's paramagnetic, and there's a susceptibility which is 3 orders of magnitude larger than the nitrogen, as you see in this table, then definitely the oxygen will take the place of the nitrogen, because it will feel more the attraction of the magnetic field rather than the nitrogen, which is basically not, almost not reacting to the magnetic field. Okay, so if you have some poles with the magnetic field, and the oxygen arrives there around, it finds the magnetic field and say, boom, I have to go there under the magnetic field. And if the oxygen goes there, definitely it kicks out the nitrogen because it has from the energetic point of view, the system has a definitely lower energy if the oxygen stays there under the magnetic field rather than the nitrogen. Okay, so if somebody has to stay under the magnetic field, is the material which has the higher susceptibility, okay, which is attracted more by the magnetic field. And then what happens? It happens that this dumbbell will rotate. Okay, so if, let's say, I'm not sure how to draw it correctly. Let's say this is. Maybe I should do some animation, which is better. Let's say this is the dumbbell with nitrogen. Then the here is the magnetic field. North, south, north, south. And then, if the oxygen goes here, under the poles, it will kick away the nitrogen, so that the dumbbell will rotate to give the oxygen the space it deserves under the poles. Okay? Then, what you have to do is to detect this rotation. So typically, on this dumbbell, you have a mirror. You send some laser, and if you move the mirror, it will reflect differently on these two detectors. So the light from the laser arrives here. It's reflected on these two mirrors, to these two detectors by the mirror. And if it's symmetric, so if the dumbbell does not rotate, it will reflect symmetrically on the two detectors. So they will get the same amount of light. If it rotates, one detector will feel less light because I'm moving away. Then I can detect that the dumbbell rotates. This is very typical principle. It's always used to detect something which rotates, okay? Or which moves, definitely, generally speaking. Then what you do is not to get the value of the rotation as an output measurement, but you use a system in the feedback, okay? Again, the principle of feedback is extremely useful when you talk about measurement. This is yet another example of feedback. Why? Because you take this signal to power some coil here, which create a magnetic field. So inject some current, and the current will generate a magnetic field. Now, in this case, you have, this is difficult to show without the possibility of having 3D. How can I do it? Like this. You have the magnetic field produced by the magnet, okay? And then the magnetic field produced by the current in the coil, okay? Now imagine that, I'm trying to look around if I have something. Something like this. The point is that I have to show it in 3D, otherwise it's not clear, okay? So these are the two ampules with the coil around it, okay? So if, now I will unfortunately I have only two hands, so I have to left down one ampules, okay? So when they rotate like this, okay? Because they have to leave the space under the poles for the oxygen, okay? It rotates like this. Then, let's say that this is the magnetic field created by the pole, and I rotate, okay? I rotate to give the space to the oxygen. So. Then I create a magnetic field which is in the same direction, but at a different angle. So, which means that now they feel the attraction to be back together because they want the two magnetic fields to be on the same, they want the two magnetic fields to be aligned, okay? So if I have these two coil around the ampules with the nitrogen and they move away, then I create some magnetic fields which try to realign back so that the magnetic field of the coils around the ampules will be aligned with the same magnetic field of the poles, okay? So eventually it will return back to minimize the energy. There will be some energy. Of course, the larger is the force which kicked away the nitrogen from the poles, the larger is the magnetic field that you have to create with this coil in order to bring back the ampules under the magnetic poles, okay? So what you measure at the end is the current that you need to inject in these coils in order to create a magnetic field able to bring back, to realign this dumbbell and have it again, and have again the ampules under the magnetic poles, okay? So you correct this rotation by feedback coil. Another principle which is used to measure the presence of oxygen, thanks to the fact that it's paramagnetic, is this interesting principle. This is sketched by Yokogawa, a Japanese company, which makes also this sensor among many other things. And basically, again, you have an auxiliary gas, which is mixed with the gas that you want to measure. And you have this structure where when you inject the auxiliary gas, you have two fluxes, A and B, which move to the right and to the left, and emit here and here the sample gas that you want to measure, okay? They mix, and then they get out from here. So here you enter with the auxiliary gas, here with the gas that you want to measure, and then here you have the sum of them, okay? The mixture of them. But in one of the 2 points where you basically mix together the sample gas that you want to measure and the auxiliary gas, there is a magnet. A magnet which has an effect on the oxygen if the sample gas contains oxygen. It has an effect because it will magnetize the gas, and it will be drawing, like it will keep there, like I'm exaggerating, of course. It will create a magnetic force which slows down the flux of the gas, a magnetic force created by the fact that the oxygen reacts to the magnetic field, being paramagnetic, okay? So here, I'm oversimplifying, so forgive me for my language, but let's say the gas containing oxygen will be trapped, by the magnetic field because of the content of oxygen. On the other side, there is no magnet, so can arrive, go, leave, mix together, and bye-bye, okay? So therefore here, you have a lower flux than here, which means that it's enough to put 2 thermistors in these 2 parts of this pipe to detect different resistance. Again, the principle is always the same. You measure the resistance. You measure the cooling effect on a resistance given by the fact that on one side you have more flux, so more cooling, and the other side lower flux because the gases are trapped by the magnetic field acting on the oxygen, and therefore if there's less flux you have less cooling, okay, so larger temperature. An alternative solution is this one. In this case you have a reference gas SP which enters here, then there is this connecting pipe, we will see later what it's useful for, and then it's divided, the reference gas enters here and arrives to the chamber on this, from this point, but also from this point. And here, in this chamber, it will be mixed with the gas to be analyzed, AP. The one, for instance, which contains oxygen. And then, in one of the 2 mixing points, you have an electromagnet creating a magnetic field. Again, here, the gas will be trapped if there is oxygen because of the magnetic force. Therefore, here you will have larger pressure because it cannot leave the reference gas will not leave, cannot leave this pipe at the same rate of this one because it is trapped by the oxygen. Okay. So you have flux here. You have larger pressure, and then here. And this means that you have a difference of pressure between this pipe, the upper pipe, pipe 1, and the lower pipe, pipe 2. And you can detect this difference of pressure in this connecting pipe, number 3, where again you can make a sensor based on which measures the flux. If you have a difference of pressure, therefore you have a flux between these 2 points. If there is no difference of pressure, there is no reason why there would be any flux of gas in this pipe. If the pressure is larger on the top than in the bottom, then therefore there will be a flow of gas, and you can detect it again with the flux meter based on thermistor. Then you can also reverse this. You can reverse the magnetic field, and you can modulate the difference of pressure. The advantage of this sensor is that in this case, the sensor is only in the part where you have the reference gas. So the sensor doesn't get in contact with the gas that you want to measure, and sometimes it might be useful. Now, speeding up because I don't have much time left. Unfortunately, as usual, I start talking at the beginning and I use all my time for that. Sensor based on conductivity or electrolytes. So now let's go to liquids. You know that if, for instance, if you take some salt and you dissolve it in water, in a solution, you have a conductivity, an electric conductivity, which depends on the concentration of the salt that you dissolved into the water. And for small concentration, this is pretty linear. So it's a good principle, good physical principle, because you can derive from the value of the conductivity the amount of salt dissolved in the solution. The only problem is it's linear, fine, we're happy. The only problem is that the slope does depend strongly on what type of salt you have. Which is pretty common for this kind of sensors. At the end of the day, you must always know what you are measuring to understand, to have, not all of them, well, sensor of oxygen, yes, but some of them don't have possibility to discriminate between different material, like in this case. For high concentration, things are kind of more complicated because at high concentration, it becomes not linear anymore, the response of the conductivity versus the concentration. And not only it's not linear, but it's not monotonic. It means that for a given value of conductivity, you have two different values. For instance, in this case, for KOH, I take the value 0.45, for instance, Siemens per centimeter, and I get that is given by two different values of concentration, about 18 and 41, something like that. So which one is determining this value of conductivity? Good luck. How to measure conductivity? You put down two plates in the electrolyte and you measure the resistance, right? That's not so simple. First of all, you can use DC to measure the resistance between these two terminals. So from the resistance, you can determine the conductivity, right? This is bad because, first of all, it might cause corrosion because you have some ions of the material which can, if the current is created always with the same terminal, the same potential, the same direction, it's basically the same principle of electropolishing. Okay, electropolishing is a process where you take away smoothly the atoms from the surface to make a surface as smooth as possible. Okay, so you are polishing out with current because the current takes away the atoms from the surface. So you can create corrosion. You can create electrolysis of the electrolyte. Also not a good idea. You can use AC, which is better, definitely, doesn't have these problems. But on the other hand, you have the problem that basically you are creating an electrolytic capacitor. So in AC, you have to deal also with the capacitance given by the fact that you polarize the electrolyte. So you don't have only the resistance in AC, but you have also the capacitance. So this is the kind of the model that you find that you have. You have the resistance that you want to measure, Rx, which is the one which tells you which is the conductivity of the electrolyte, and we are happy about that. But you have also the capacity, the geometric capacity, because you have two electrodes, you have a capacity. And this can be calculated more or less because you have the geometry. Of course, there are some border effects, but if this is large enough, you can neglect about the border effects. Then you have the capacitance of the cable. And then you have the capacity of polarization, which is given by the fact that you polarize the electrolyte and you have an electrolytic capacitor, in fact. Of course, you don't want these capacitances because your ultimate goal is to measure the resistance. And but you see that you have the capacitance of geometrical capacitance and the capacitance of the cable, which are in parallel. So you want this impedance, which is 1 over j omega c, to be as large as possible. And you want this impedance to be as low as possible, okay? Because here we are in series, so we want this impedance to be basically 0, so that here you have a short circuit, okay? So if you have, so the impedance of a capacitance is 1 over j omega c. So 1 over j2 pi fc, okay? Which means that here we want this capacitance, this impedance, to be very large, okay? So we have to make a choice of frequency that makes this impedance very large. But on the other hand, we want this impedance to be very small, because it's a short circuit. So we must choose a frequency which simultaneously makes this capacitance very small. So you have two opposite requirements for the frequency. So from one end, you want a frequency which is large enough. From the other end, you want a frequency which is low enough. And you must find a trade-off so that the frequency will give you, the frequency that you choose will give you an impedance which is an impedance for the geometrical capacitance and the capacitance of the cable sufficiently large to appear like an open circuit over this resistance, and simultaneously the impedance of the polarizing polarization capacitance to be small enough to be a short circuit. Okay. You can partially solve this problem if you, instead of using two plates, use some point electrode. It's like here, and we have an example. This is just an enlargement of the tip of this electrode here. Typically use 4-point electrode. 4 points system, as you remember, is some system that you use for measuring like a very small resistance, because it takes away the resistance of the cable and the contact. In this case, we use it for a similar purpose, because here you have you inject a current here, and you get the voltage, and you get rid of the extremes of this potential, which are extremely nonlinear, given by the polarization of the electrolyte around the terminals. And so you get only the linear part of the response, okay? So here are the 4 terminal, and you get advantage of this, on the fact that taking only the central part of this potential, you get only the linear part of the response and not this non-linear part. So partially you get rid about this capacitance here, okay? Let me see how many slides I still have. Ooh, I'm not sure I'm gonna end today. So I wanted to end everything today, but evidently I don't have time enough. So yes, definitely I'm not gonna end today. So I underestimated my speed of talking. So I would continue tomorrow with contactless sensor of conductivity. Then we will talk about other sensors, and then we make some exercise. Okay. So this I originally wanted to be the last actual lecture about before Christmas, but evidently I have to continue tomorrow. Okay, so sorry if I finish 3 minutes before the end, but if I start this topic here, I will continue for a long time, and I definitely cannot manage to finish. Okay, so tomorrow we will finish the chemical sensors, then we make some exercise, and then I promise I will go back to you. Somebody is waiting response for exercises for laboratories that they sent me time ago, and I didn't have time enough to work on that, but I promise after Friday we finish the lecture, so I have 100% time to dedicate you and the answers that, of course, you deserve. Okay, so if there are no questions, I would finish the lecture here and see you tomorrow.